Hello, so today we are presenting large neuroacoustic models for frequency-guided music therapy. And these are the group members. So these are contents for presentation. We have introduction, related work, problem statement, research questions and objectives, research contributions, methodology, dataset description, results, conclusions, and limitations. So the recent trends in music therapy show that the countries that are involved majorly in the research are the United States of America, England, China, Italy, and the Netherlands. These are the countries that are leading the rest of us in music therapy research. And then music therapy through methods like improving cognition and studying like heart rate, through methods like that, research therapy is used for relief in both neurological conditions like stroke, dementia, Parkinson's, and autism spectrum disorder, and also in psychological conditions like depression and anxiety, stress and anger. So music recommendation AI systems these days use sensors attached to wearable devices, that's like smartwatches, and then you use user feedback, lyrical content, and acoustic features of the songs. That's the the timbre of the voice of the song, the frequency, the tempo, and then they use those features to determine what songs the user would like to listen to. And we move forward and talk about the problem statements of the project. Now, the domain application problem is that currently music recommendation systems use majorly popularity and listening history to determine what songs the user would like to listen to. And they don't account for the psychological conditions and real-time emotional states. So psychological conditions like someone that has depression, has anxiety, and then real-time emotional state indicators like facial expressions, that to determine whether at the current state the person is happy, sad, stressed, and then so they help with the music, but they are not useful in the medical health field. And then we talk of the computational problem. This computational problem, it incorporates the project incorporates psychological and neurological condition profiling. That's they profile your music taste based on your psychological and your neurological conditions, and then integrates real-time affective cues from facial expressions. That's through the facial expressions and wearable devices to determine whether you're stressed, angry, sad, happy, disgusted, and then recommends music that is not just personalized for entertainment, but also it's therapeutically aligned. So our objectives for the project are to develop a large acoustic generative model that produces therapeutic music, adapting to both long-term psychological conditions and real-time emotional states. It produces music that is taking into account that if a person is depressed and also sad, they are going to produce a certain kind of music that is going to help them in both taking into account both those conditions. And then to gauge emotional state from facial expressions and biometric data, that is to gauge whether the person is sad, happy, disgusted, neutral from their facial expressions and through their biometric data, that's heart rate, blood pressure, something like that. And to design and implement a feedback-driven generative architecture that integrates reinforcement learning guided by expressions and biometric signals. So this is such that the system would learn your facial expressions, and then you feedback the system gets back is if the system is rewarded, if it's wrong, the system is penalized, and then it would learn like that. And then research contributions, we selected a data set, the NSYNC data set, for extracting frequency, harmonics, and human rhythms from the songs. And then we selected the neuroscientific and clinical literature data set. This is to study the acoustic features of a song in relation to the therapeutic effects of a song. We integrated these data sets so they can work together. And then we fine-tune the deep face model in order to recognize emotions from different images. The next person. This is slide 7, sorry. Samuel?
Okay, Ariat, if you're ready, you begin your presentation for slide 7 up to 11.
So I start from here.
Yes, start from
Yeah.
here.
Explaining the methodology and system architecture. For our system, the input would be the facial expressions, whereby the system feeds the psychological state into the system. Like it can look at the brain activity, then it relates it to maybe the heart rate, the stress levels, so that it's able to identify maybe the current situation or the current mood that its user is in. Then the second step would be face detection and alignment. After detecting the mood that the user is in, then it can align it to a certain, maybe a certain disorder or a certain health issue that maybe the user is facing. Then it does the feature extraction, whereby it extracts the features, and then it's able to classify the emotions. Then it predicts the final, like the final, maybe the final disorder or the final mood. Then it recommends or suggests songs according to that mood. Wait, I share again. Then for the dataset description and exploratory data analysis, for the dataset description, we integrated 2 datasets. That the first one being the NSYNC, which works with large audio datasets, and then it's used to extract frequency, harmonics, timbre, and rhythm. Then the second one was the neuroscientific and clinical literature, which curated studies linking to acoustic features, to the therapeutic effects, the acoustic features being frequency ranges. Then it links them to the effects, the therapeutic effects, such as the oxytocin, serotonin. Then for the EDA results, I was able to attain histograms showing the tempo distribution, frequency distribution. Then the few key insights would be that NSYNC samples cover broad frequency ranges. Then there is tempo variation, timbre diversity, So the integration with clinical findings shows clear effect relationships. For example, the low frequency high tones reduce cortisol, and then the rhythm percussions enhance the dopamine release. The next slide. I was able to get some graphs. This first graph shows the frequency analysis, in that it shows that different ways frequency range is distributed in case of unattained emotion or unattained disorder, maybe like when you're trying to detect like autism, sleeping disorders, anything like that. And then this other graph is showing the distribution of frequency ranges. Next slide. This graph shows the variations between rhythm and harmonics. This table shows the output results and discussions, in that we look at the music file, the frequency, rhythm, harmonics, timbre, brightness, like the results we got from the feature extractions. Next graph. Then this graph shows the expected results and discussions. So like I've shown in the previous slides, we got the output we got, then we compared them. In this graph compares them to what was expected. So for low frequencies show strong relaxation, then the mid alpha show good mood elevation, high beta show moderate focus, then the very high gamma show cognitive engagement but less therapeutic effect. The next one. And then this last graph shows the therapeutic responses. The first graph shows the sample with therapeutic targets. So if we are using if the system is using the therapeutic targets, it works at a 45%. Then if it's using without the target, it uses the 55.3. Then the other one shows the different types of hormonal responses. Yeah, that is it that's where I stop.
Okay, thank you, my previous speaker. As I conclude, I'm going to conclude by talking about the models we use to train, to extract the features from those different data sets, and also data sets we obtained. So as they have discussed, that we got musical data sets, whereby in those music data sets we had to extract in those features like the timbre, the brightness, whereby the brightness is just the average frequency using these two frequencies, because we had raw music like songs, and then we had to extract in these different features like frequency, rhythm, or harmonics, timbre, brightness, whereby brightness, as I've said, is just the average frequency. Yeah, and so the different models we used, because our data was just raw data, and then we had to filter out and also obtain these frequencies. So that we design a model so that we obtain the frequencies, and we use the reproduce model to navigate into the song, then obtain those different frequencies. And also, as you can see, I had to form a system to model like if at all someone is sad or happy, then these are the frequencies which are going to be aligning to their mood. So we select this specific music based on whether the person is sad or happy, then we attach them to a given frequency. Yeah, we're just demonstrating how we developed our product. We had to generate personalized therapeutical music targeting the specific brain regions, whereby we're trying to support people having anxiety, depression, to recommend them to music which will be able to elevate their mood. Yeah, and the key features are just mapping rhythm, frequency, timbre to those therapeutical effects. And then the system links those music features to the neuropsychological outcomes and then recommend music. So the accessibility will be, this system is going to be integrated on the phone, like for a phone application, whereby someone can download it and then they open their camera, record their face, and then the system is able to navigate through their face. And then this, we used facial data, whereby we used the data set, and then we used deep face. We fine-tuned it in order to extract emotions from a person's face. So deep face is one of the models we used, but we had to fine-tune it such that it works well with our system. Then, as we conclude, some of the limitations we're facing, some of the data is raw and not cleaned, so we're facing a challenge of cleaning it and also having very diversity inputs, whereby someone can be having a face which is sad, but when they are happy, deeply, just that's how they are just having a sad face. So those are some of the limitations, and also clinical validations, because the data we're having, we have to fine tune our models, but then obtaining these clinical validations, because this area has not been, like, not many people have been focusing on this area, so getting these clinical validations is also not easy. And some of our conclusions, this system, when it's done, it will be able to produce personalized recommendations based on people's emotions, promising for both wellness and clinical applications. But then we still need to further test it such that it reaches the maximum goals which we want to attain. So our next steps are going to be to improve the system by using big data sets, so putting in more data in order to increase its accuracy, and then integrate it with real-time brain feedback for adaptive music therapy. And this is going to be done through reinforcement learning. And then we will have to conduct clinical trials in order to validate our system. And then we'll have to explore combining music therapy with other interventions, e.g. meditation, in order to make our system to produce the best outcomes. And then we have to develop a user-friendly application which will be able to run our system. So those are our next steps. Thanks for listening. Don't forget to subscribe and share, also to like. Thank you.